Well, hey folks, how y'all doing? This is our second day of the exam. Just as a reminder, the exam is tomorrow. Um, we'll go live at 9 a.m., so you should be able to download anytime after 9 a.m. And then you have to upload your solutions by 9 p.m. And so that gives you plenty of time to budget your schedule. This is You may bring a formula sheet. But you may not use any online resources. Um, so big red, I'll make red. No X, no online resources. Don't collaborate. Work alone. Um, all right. Um, let's go ahead and get started on the rest of the review, though. Good luck on the exam. So, let T be a tree with two or more vertices. Proves that T contains at least one leaf. So, that's, I think, pretty obvious. I mean, that if you start with a parent, parent can have childs, and then if these aren't leaves, then they have to have their own child's, own children. And then if these aren't leaves, they have to have their own children. We would have a problem if there wasn't a leaf somewhere on the tree. So how would we go about proving this? So there's a hint about the degree of a leaf. So suppose T had no leaves. Then the degree of every vertex is greater than or equal to 2. And so the total degree is greater than or equal to 2 times the number of vertices. But by the handshaking lemma, we know that the total degree is always 2 times the number of edges. And therefore, 2e is greater than or equal to 2v, and so e is greater than or equal to v. Why is this a contradiction? So we have more edges than vertices. This is a contradiction. Because in every tree, the number of edges is equal to the number of vertices minus 1. This is something we've talked about before. And so it's not possible for the number of edges to be bigger than the vertices and to be 1 less than the number of vertices. And so since v minus 1 is not greater than or equal to v, then this violates the handshaking lemma. Okay? All right. So let's move on. Prove that any graph with an odd cycle cannot be bipartite. So let G be a graph with a cycle containing 2k plus 1 vertices. So here I'm using that odd numbers can be written in the form 2k plus 1, where k is an integer. So here's the idea. We have some cycle where my vertices start v1, v2, v3, v2k plus 1, v2k, and then go back the other way around. So I don't know how many edges are in a cycle, but I know it's an odd number. So suppose v1 is in the set X, then v2 must be in the set Y because the graph is bipartite. And then v3 has to be in X and v4 has to be in Y. You start to see what's going to happen here by induction. V sub I is in X for all odd I, and VI is in Y for all even I. But now the edge right here at the very end from v2k plus 1 back to v1 connects two vertices in X, and so G is not bipartite. All right, let's look at number 14. Let G be any connected graph with a cycle. Okay, so we have a connected graph with a cycle in it. And E is some edge that's part of the cycle. Prove that G minus E is still connected. Okay. So let A and B be the endpoints of edge E. So here are my two endpoints, A and B. Okay. All right. So in order to be connected, we have to have a walk from any other vertex to any other vertex. Okay. Let U and V be vertices in G. And let W be a walk from U to V. If W does not contain E, so if it doesn't contain this edge E, then W is a walk in G minus E as well. If W does contain E, so I'm walking from some vertex U to some vertex V, and I've identified this walk that uses the edge E. What I'm going to propose is that we can replace this edge with the reverse of the cycle and then walk back to V. That is, now that's not a very efficient walk because I'm using some edges more than once, but that's still a walk from U to V. So if W does contain E, replace E with the rest of the cycle. And now, and then so we have the walk containing E, we've replaced E with the rest of the cycle, and therefore the new W, let's call it W prime, is a walk in G minus E. And therefore, any pair of vertices we can still connect together even without E, and therefore G minus E is still connected. All right. Let G be a graph with vertices from 1 through K. Prove that the statement VI and VJ have the same degree is an equivalence relation on the same set of vertices. So we have to check three things. We have to check that it's reflexive. We have to check that it's symmetric. And we have to check that it's transitive. So reflexive, we begin with just a statement, let VI be any vertex in G. For symmetric, we begin with the statement, let VI and VJ be any two vertices in G. And for transitive, we begin with let VI, VJ, VK be any three vertices in G. So reflexive takes one vertex, symmetric takes two, transitive takes three. For reflexive, we just want to show that VI has the same degree as itself. Since the degree of VI equals the degree of VI, that's kind of silly to say, the relation is reflexive. All right, for symmetric, now we're going to make an assumption. Assume that the degree of VI is equal to the degree of VJ. Well, therefore, the degree of VJ is equal to the degree of VI, because the equal sign is symmetric, and so this relation is also symmetric. Symmetric is if we have the relation in one direction, we have the same relation in the other direction. So the relation is symmetric. For transitive, we assume that the degree of VI is equal to the degree of VJ. Those two are equal. and the degree of Vj is equal to the degree of Vk. So then, how will we show this? That the degree of Vi is equal to the degree of Vk? Well, there are a couple of ways of saying that, but the easiest one is just to say that being equals is transitive. But then here's a fancy way of doing this, but it's overly fancy. We don't really have to do this. The degree of Vk minus the degree of Vi is the same thing as the degree of Vk minus the degree of Vj. I'll bracket that together, minus the degree of Vj, Vi, minus the degree of Vj. So when we subtract these, we get the degree of Vk minus the degree of Vi, and we get the negative of the degree of Vj minus the negative of the degree of Vj, which cancels out. So these two things are equal, but this equals 0 because Vj and Vk have the same degree, minus 0 because Vi and Vj have the same degree. And so that equals 0, and therefore the degree of Vi is equal to the degree of Vk. And so the relation is transitive. And so we've proven all three parts, and therefore we have an equivalence relation. All right. Okay, let's construct the proof or sequence for the tree that is shown here. All right. So let's take a look at that.